But essentially what we'll be talking about today is the Arrhenius theory of acids and bases and the Bronsted-Lowry theory of acids and bases, and therefore we'll be talking about conjugate acids and bases and proton transfer and a proton donor and a proton acceptor, and we've done this all last year. This is 100% review. It's actually taken from my notes that I give out last year. So title, good thing to have. I think everybody's got it. And properties of acids and properties of acids, that worth writing down? I think so. Let's write this down then, just to get it into our minds. But I'm not going to be going in great detail. We're not going to be doing little labs where we can test the pH with pH paper, right? We'll be doing that with pH meters, and we'll be doing it in different situations. Again, last year when we first introduced this, we did a lab where you did put all those different indicators in there, and we used the pH meters a little bit. But now we want to get to applying this to equilibrium systems. Right, recall electrolytes mean that they conduct electricity in solution. We put a conductivity apparatus in there, it's got a little light bulb on it, the little light bulb will turn on. Okay, so a quick reminder of the Arrhenius definition. Let's just write down, the first two bullets there. Don't worry about the third bullet here. Don't write down the fact that H plus is responsible for the characteristic properties of all acids. I'll be reminding you of that as we go along. But Arrhenius believed that those H pluses, that's what makes the litmus red, and that's what makes the sour taste. Again, don't worry about the last bullet. I think the last bullet is one of those obvious statements to you guys. The greater the concentration of the H plus, the stronger the acid. We'll be talking about pH tomorrow. We'll review all of that stuff tomorrow, and that'll come into play. So essentially, they're molecules that fall apart to produce H pluses in water. Some examples, just put EG. Too fast? Am I too fast? You're not writing all the bullets, are we? Just want these first two bullets. That's all right. It is too fast. Tell me to slow down if I do go too quick. Good? All right. So don't put examples, just put EG. We don't need to do them all. We'll do number one. Right, and I think we know this. This is going to get me H plus aqueous plus Cl minus aqueous, right? They ionize. Don't worry about number two. The H is going to fall off of it. Let's just look a little bit at number three. This is a representation of acetic acid. Acetic acid is a weak acid. We will be looking at this example quite a bit in the near future. When acetic acid is written in this particular fashion, it is the last H that we call the acidic H. That's the H that's falling off into the water and when it's ionizing. So when we write the ionization for acetic acid, CH3, COO, I even separate out the O's, minus aqueous plus H plus aqueous. All right? So it's the last H that falls off of that that acetate ion. Okay? Arrhenius acids. They've got an H in the front, except for acetic acid, and that H falls off in water. Properties of bases. Change indicators of characteristic color. We'll be looking at indicators in far more detail this year than we have in the past. In the past, we talked about phenolphthalein. Recently, you looked at bromethymol blue, litmus, obviously, litmus base blue. Did I show you the video last year of the funny guy who said blue to red acid? Blue to red acid. That's good stuff. Okay, that 1970s demonstration guy. Entertainment right there. We'll talk about indicators in more detail later on in terms of an equilibrium situation. There are also electrolytes, pH above 7. Again, nothing earth-shattering here at this point, I believe. Okay. So again, Arrhenius definition of a base. Just write the first 2 bullets. Again, Arrhenius, very simple definition. If it's an ionic hydroxide, if it's got hydroxide on the back end and that hydroxide can fall off and dissociate into water, then you have a base. Again, don't worry about the last 2 bullets. Simply says OH is responsible for the characteristic properties of bases. I think we know that, and that's still an important statement, and I'll be writing that down in a different location. And again, the greater the OH minus concentration, the stronger the base is. And I think we know that as well. Okay. Again, a couple of examples. Let's just simply do the first one. It really doesn't actually. Yeah, no, we'll just do the first one. So it's fine. No, I changed my mind. I want to do the first 2. Na plus aqueous, OH minus aqueous. And if I've got something like magnesium hydroxide, Mg plus 2 aqueous. And the reason I wanted to do this is when we're dealing with bases, sometimes if we've got an ionic base, we'll get 2 of those OH minuses. I guess we didn't need the brackets. It doesn't matter. Aqueous. Ammonium hydroxide, again, NH4 and OH. It's not worth writing a third example down. So that's an Arrhenius base. If it has OHs in it and those OHs fall off in the water when they dissolve, we will have a base according to Arrhenius. Okay. Definition of a neutralization according to Arrhenius. Yeah, we can write that down. We use this type of reaction when dealing with a titration. We're going to be looking at titrations in more detail at the end of this unit. But again, even though we're going to be looking at titrations from an equilibrium standpoint, the beginning calculation of any titration will be simply a neutralization. We always still have to do that I want to say basic, but that's not what I mean, not base, but essential, simplistic, right? Neutralization. We have to trade the H with the metal and make water and some kind of a salt. And then we analyze the titration in more detail. So even though we're going to be looking at titrations in greater detail, we still always start with the fundamental reaction like this. And hopefully you've completed it. We're going to get H2O liquid plus NaCl aqueous. And I got that flipped around from the salt in the water. You know that. You get the idea. I should have did it the other way, but anyway. One H and one OH produces one water. Sometimes it's 2 to 1, but you guys know that from the lab you just finished. We had a 2 to 1 there with the calcium hydroxide. You can have 3 to 1 too, I guess, if you had phosphoric acid and a base like that. Okay, again, nothing new here. Yeah, you can write this down. We'll write down. we'll write down this whole thing. And you can dissociate those salts and break them into their ions. The last two bullets are a problem with Arrhenius' theory, because it turns out that some salts are actually basic salts and some salts are actually acidic salts. But according to Arrhenius' definition, if they don't produce H plus or OH when they dissociate, then they're not acids or bases. They should have a pH of 7. And that's an error. And we're going to remedy this. We're going to use our knowledge of acid-base equilibrium to take care of this. And that's why it says Arrhenius predicted. This is not necessarily the case. That's why we call it an Arrhenius definition of a salt, because salts can behave differently than this. So that is not necessarily 100% true, especially these last two statements. These statements are true, but after we'll learn what happens to these ions. Do these ions interact with water to do something? And the answer is yes, they do. Okay? Now, next I think, and I don't know, let's hold off on writing this down. Problems with the Arrhenius definitions of salts. Some salts are acidic even though they don't dissociate to produce H+. I just mentioned that. Let's not write this down. So even though they don't produce H+, we're going to see how they can produce H+. So there are issues with the Arrhenius theory. Some salts are basic, right? So some salts are acidic, some salts are basic. NH3 is basic even though it doesn't contain OHs as part of the chemical formula. And it is an electrolyte, even though it isn't an ionic compound. So we've got a bunch of scenarios, and I talked about this last year as well, where we cannot explain acid and base properties of many compounds using the simplistic Arrhenius theory. So, and again, I don't think that's worth writing it down. Why is this? Arrhenius ignored the solvent, usually water, recognizes that in most acid-base reactions, a proton is transferred from one reaction to another. And that brings us to the Bronsted-Lowry theory, and you can continue. So the Bronsted-Lowry theory is a more complete of an acid-base theory, because it can explain those problems that were just on that previous slide. There is another theory beyond the Bronsted-Lowry theory that you will encounter in university. It's called the Lewis theory. And it's a little more, it doesn't necessarily associate itself with changing litmus and being sour. It has to do with electrons being shared. And it explains a very few minor little details. But you don't have to worry about that here. You'll get it proposes. It's pretty straightforward, but we're not going to worry about it here. It doesn't fit in with what we're doing in equilibrium. So the Bronsted-Lowry theory, in the Bronsted-Lowry theory, we have a Bronsted-Lowry acid as an H plus donor. So we say then that HCl is an acid because it's going to donate an H plus, or an H3PO4 is an acid because it can donate an H plus. And on the flip side, yeah, my animations aren't working, so it's not a big deal, but I think we saw that last year. On the flip side, we have a Bronsted-Lowry base as being a proton acceptor. I really don't like that or in there because it's really more of an and or. In order to be a proton acceptor, it's got to have a lone pair of electrons. It's that simple. And that's that other theory that I kind of mentioned. The Lewis theory of acids and bases, which you've never heard of before, deals with this lone pair of electrons. Instead of it thinking about the proton, thinking about the electrons. Not a big deal. It's kind of neat, and if you want to look it up, it's kind of cool. But we're not worried about it here. And or a negative charge. To say just or, to say that F minus is the example, well, F minus is right full of electrons, right? The charge on an F minus, or the Lewis diagram for F minus is looking like this, right? So to say that or it needs a negative charge, it's really, a negative charge is favorable because it's going to attract the H plus to it. It's going to like draw it in because of the electrostatic force between the positive and the negative charges. So the negative charge isn't a requirement. It just makes it a little more attractive to an H plus. It's going to have electrons around it. If the thing doesn't have lone pairs of electrons around it, there's nothing for the H plus to latch onto or to stick onto. Okay? So Bronsted-Lowry as acid-base donors and acceptors. Let's write down this little definition. Again, my animations, I don't think they're working. It said that it wasn't going to function. Nope. Back up there. So now, as I stated last year, in terms of Bronsted-Lowry, there's a big difference between something being a Bronsted-Lowry acid and being acidic, as well as a Bronsted-Lowry base and being basic. So we just need to use our Bronsted-Lowry acid-base reaction to figure out whether it's going to be acidic or basic. Do a little freeze move here because I want to take a look at what's on that next slide. That's interesting. I don't know why I put it like that. Kind of goofy. So let's take a look at a Bronsted-Lowry acid-base reaction. This is exactly the same example that I would have given you last year. I'm going to draw it out with the electron pairs, and then I'm going to write it a little differently. So here we have our example, and don't mind that. I don't even know why I used the note feature instead of actually just typing it into the part note. I'll write down what I want you to put here. But let's just take a look at this. Starting with HCl and water, right? We put HCl into water. That H plus falls off and is transferred onto a lone pair on the water molecule. Now, I'm not expecting you to, I do want you to write this, but I'm not expecting you to write out water like this each time. This is really more of, here's the way it kind of looks, and then after that, we'll just write down the formulas and we'll just, in our mind, have an idea on what's taking place here. So what happens here is this guy is transferred over and attaches onto a lone pair. Right? The H plus is attracted over. What that leaves us with is a Cl minus All right? And I could draw the Lewis diagram for it, but I'm not that interested in it. And then this one I will draw the Lewis diagram for. Now I've got the OH and the extra H that was added on with an H there. There's a lone pair left. And this thing now has a positive charge. And if I were to rewrite this, HCl plus H2O, and actually, and I'm going to just bring this in, this is also an equilibrium situation. Cl minus plus H3O plus. All right? And what I was doing here is I was going to remind me to tell you, and you don't need to write that down, but this thing right here, and this is what you can write down, what I'm going to write here, H3O plus, we learned last year, is called the hydronium ion. Hydronium ion, all right? And if this thing is a product, if product, then we say it's acidic, right? It's the thing now that we know that is responsible for making acids behaving as acids. So if you get an H3O plus as a product, we say that it is an acidic situation. That will turn litmus red, that will taste sour, that will change the pH to less than 7. So now, instead of H pluses, you're looking for H3O plus as a product of a Bronsted-Lowry acid-base reaction. Okay? So HCl is our Bronsted-Lowry acid. I was actually calling it a Bl acid last year a little bit, right? I might have put it down like that. This is acting as a Bl base, and it transfers over. But remember, being a Bronsted-Lowry acid doesn't necessarily mean it's going to be acidic, right? And I also said, you know, you might have the question, hey, doesn't an acid plus a base make neutral? It does according to the Arrhenius theory, but in a Bronsted-Lowry situation, an acid is just a donor, a base is just an acceptor of an H plus, and if I get H3O plus as a product, then I have an acidic situation. Okay? That's starting to come back a little bit. It is very, very much review. Same with this one. This time I'm not going to write this whole thing out here. Let's just go with NH3 plus H2O. Don't write down all of the Lewis diagrams. Just write down NH3 plus H2O. Now in this case, you might ask yourselves, and I said this last year, which one's going to give up the H? I'm going to show you in a couple of days how you know which one gives up the H. In this case, I'm telling you that this particular H on the water is going to end up attaching to the lone pair on the NH3. So in this case, the water is donating. If that's the case, again, this is an equilibrium situation, we're going to end up with NH4 plus aqueous and OH minus aqueous. And the reason I'm using this example, and I know I've inverted the colors, it's not a big deal, but, and look, I've got it written down here, but you can write it underneath. This guy here, we know is the hydroxide ion, and that's our good old Arrhenius definition, right? Now it's hydronium ion and hydroxide ion, and the hydroxide ion is the thing that gives us the properties of being base. So if it's a product, right, of the reaction, then we say it is a basic solution. It will taste bitter. It'll feel slimy. It will turn litmus blue. Did I already say that? I don't remember what I'm saying anymore. And again, I believe I said that exactly the same way last year as well. Very much review. In actual fact, the depth that I go into it last year is not required for the grade 11 course. But it makes my life a lot easier when I get to this point because I want to get to the equilibrium applications of this stuff. I want to get to the new stuff. Okay. Amphoteric, yeah, this is good stuff right here. Actually, write down the definition, okay? Don't write these examples. You could put e.g. see previous examples H2O. Because if you look at your previous two examples, you'll notice that water was behaving as a base in the first example, and water was behaving as an acid in the second example. I think you should have that labeled somewhere, and if not, we'll go back and label the acid and base in that second example. So don't write these two down. An amphoteric or amphiprotic substance is a substance that can act as a Bronsted-Lowry acid or a Bronsted-Lowry base under different conditions. It depends on what it's up against, which determines which is going to gain or lose, or whether it's going to gain or lose a proton. If I go to the previous example, this guy was acting as the acid, and this guy was acting as the base. You can add that in if you didn't have that, because it's donating the proton. And in the previous example to that, the water was now acting as the base. So water has that ability because it has a lone pair, and it also has H pluses. All right? Anything that has that situation can do that. Can be an acceptor or a donor. So if you saw the previous two examples, excellent. Let's talk about another example here. I do want you to write this one down. So whether you call it number 2 or whether you just put HCO3 minus. So what we have here is a bicarbonate ion. Bicarbonate, and usually I like to write these out so that you can have a feel for it as I'm writing. But if I take a bicarbonate ion and I mix it with a base, something that we call an Arrhenius base, something that's basic, then that bicarbonate ion will transfer an H over to that OH. It'll become a carbonate ion in water. If I put a bicarbonate ion with an acidic substance, something that, was acidic, has litmus turning red, etc., etc., this H will transfer over to here. It actually gets attached onto the O, but I'm going to just bring it over there to the H. The O actually has a lone pair on it, which allows it to stick to it. And we turn it into that guy there. I want to cover a couple of terms as well here as I'm doing these examples so that we can cut through a few examples that are a little later on. First, just a reminder, what is the HCO3 behaving as in this situation? It's the donor, so this is the acid, this is the base, right? And remember, these guys are equilibrium reactions, which means I can actually have that reaction go in reverse. If the reaction's going in reverse, what does the CO3 minus 2, the carbonate ion, how is it behaving if the reaction is heading back that way? Is it an acceptor or is it a donor? Is it an acid or is it a base? Sean? Yeah, it's a base. And does anybody remember what we called that opposite base? We didn't call it an opposite base. Starts with a C, correct. Conjugate base. Conjugate base. I'm just going to put conjugate. Because in a moment I'm going to define conjugate acid-base pairs, and instead of writing down a great big long example, we can look back at this. And then what does that make the water? Yep, the conjugate acid. Conjugate acid. All right. Same with here. Let's finish off by labeling all of these guys. What is the bicarbonate this time? Yeah, it's the base. It's the acceptor. Base, acid, and right away you can determine what the other guy is going to be because it becomes opposite to it, conjugate acid, and then the conjugate base. Conjugate base. All right? This also has a little application. Let's say you spill some substance, you're cleaning the bathroom, and you spill some liquid on the floor, and you're not sure whether it's basic or acidic in characteristic, and you don't want to dive in there and clean it up because you might hurt your skin. You can always get some baking soda, sodium bicarbonate, spread it on there, and no matter whether it's an acid or a base, that bicarbonate will neutralize any H pluses or OHs that are there. Okay? Other examples of conjugate acid-base pairs, right? Other examples of amphoteric things would be something like HSO4 minus. Anything that has an H and the negative charge can either be a donor or an acceptor, right? So if we look at the phosphate ion, if I had HPO4 minus 2, right, that could be the case, right? That's usually minus 3, but it's got an extra H. Or it could even be H2PO4 minus 1. It's got the negative charge. It's got room to take an H or to donate an H, right? And I'm just going to put here, etc., because you could then have hypophosphite and all that. All those different guys in there could be amphoteric. If it's got an H and it's got a negative charge, then it can accept or it can donate. Again, very much review. I'm not noticing the same looks of panic as I saw yesterday. Did I just say that? Ooh, that was mean. So acid-base reactions are reversible. I've been implying this. I could probably jump over this slide, but you guys dove in and started to write, and that's okay. If the acid is weak, actually, you know what? They're all. It doesn't even have to be just that if it's weak. All Bronsted-Lowry acid-base reactions are reversible. They're all examples of equilibrium situations. The weak ones are where the equilibrium sits somewhere in the middle. That's what makes it interesting. If it's really strong, the equilibrium sits hard right. And if it's like super, 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 super weak, which we will talk about, super weak, then it sits to the left. So they're all actually examples, all Bronsted-Lowry acid-base reactions where we have a proton transfer are equilibrium reactions. And again, all I wanted to do here was to just restate, again, there it is there, that this is the acid, this is the base, and again, here we're going to have our conjugate acid, and here we have our conjugate base. And a quick little definition here, conjugate, and I have to say it that way, acid / base literally means opposite acid / base, right? And there's my little note to myself. They differ in formula by an H plus, right? They differ in formula by 1 H plus. Okay? CH3, COOH, and CH3, COO minus, we would call a conjugate acid-base pair. All right? Nothing new, except I spread it over 2 lessons, I think, last year. Now I'm jamming it into 1. That's just an example. Let's not write this stuff down. I think we get the idea. Let me get to giving you some practice problems and some stuff. Identify the conjugate acid-base pairs in the following reaction. Well, let's identify them first. My H2PO4, what's it behaving as in this case? It's behaving as, yeah, it's behaving as the acid, right? That's the base. OH is the best base, so it's always going to be the base. But I'm going to show you how to be able to tell what's going to be taking place. Therefore, this is the conjugate base, and this is the conjugate acid. So my conjugate acid-base pair is H2PO4 minus and HPO4 2 minus, along with OH and H2O. But I think we get the idea. All right? They're pairs. These are the exact same scenarios that I gave you. Like I said, it's the same lesson, except I've transferred it into this. You know, given the formula of the acid, if we're saying this is the acid, what's the conjugate base? And we'll just do this quickly and orally. I don't think you need to write it. If you'd like to write it, you can. What do you got? Yeah. If this is the acid, it's losing it, so it's OH minus. How about this one? What is the conjugate base for this one? Yeah, Tyson? I need a charge. -1. And if that's acting as an acid, what's its conjugate base? Pause for thinking. Jenna's staring at it. She's got an idea. What do you got? Well, if it's an acid, is it a proton donor or a proton acceptor? It's a donor. So this thing's going to give up an H+, right? What's going to be left after it gives up an H+? An S, but it's giving up an H+. So what's the final charge going to be after it throws that plus charge away as well? It's -1 to start with, and it's given up the H+. -2. -2. Excellent. We extracted that information from Jenna's brain. I knew it was there. All right? And the opposite situation, again, no need to write. If the water is behaving as a base, a proton acceptor, what's the formula of the conjugate acid going to be after it's accepted it? Yep. H3O plus. How about HSO4 -1? What's it going to be? Yep, Sarah? Yeah, H2SO4. And NH3 after it's an acceptor. Yep, Kristen. NH4 plus, right? NH4 plus. Charges are very important on this stuff. Okay, what are we at? We're at 25 of 31. We're going to make it. What do we have here? Complete the following acid-base reaction. Only one change. Identify the conjugate acid and base. I think we've done this to death. So let's stop there. What, 26? Oh, those are answers. All right. I'm going to give you the question sheet, and there's some textbook work. And you've got plenty of time to work on this. This is a sheet. I don't think it's exactly the same as last year's sheet, but the textbook doesn't have a whole lot on this, as you can see. And the text reference on this page is obsolete. It is old textbook reference. That's why I give you new textbook reference right there. That's the new book. And the questions on here are old book, so don't go looking for them. And I'm going to just stop this recording before I hand this out.